Hello everyone, and welcome to Linux Forensics here at Pen Tester Academy. In this video, we're going to talk about how we go from an inode to a file that it represents. So we're going to start out by talking about the inode block. So in the inode, we have a block, and often we'll hear people talk about this block, and they will say it is a block of 15 pointers. Now, it is more correct to say that it is 60 bytes of data. So what's in there? Well, if it's a regular file or a directory, you will have direct and indirect blocks sometimes. The most generic case, that's what you have, but we'll see you can have other things in there as well. Now, if you have a symbolic link and it is not very long, if you can store it in the 60 bytes, it's stored right in that spot. That way you never have to leave the inode for a symlink. If it's inline data, there's a flag that is set in the flags, which we saw in a previous video, and then the first 60 bytes of the file can be stored in the inode. This allows you to store small files entirely within the inode. It can also speed up certain operations for longer files. Finally, if you have an ext4 file system, you can also have something called an extent tree. And we'll talk about what this means, but essentially it lists data runs or sets of contiguous blocks. So let's start with the simple case. In the simple case, these 60 bytes are used for 15 block pointers. The first 12 of these pointers point to data blocks. So if we have a standard 4K block size, this means I can have up to 48K in a file in these first 12 blocks. The 13th block is an indirect block, and what it has is a block that contains pointers to other blocks. So if I have a 4K block size, and each pointer is 4 bytes, I can store 1K of pointers to 4K blocks. So this allows me to store a file that is as large as 4 megabytes plus 48K. So I can store quite a few files in that space. If that's not enough, in the 14th spot, I have a double indirect block that points to a block containing block pointers. So now I have 2 levels, and each level has 1K. So I have 1K times 1K of pointers, and again, they all point to 4K blocks. So this allows me to store up to 4 gigabytes plus 4 megabytes plus 48K using just this part of my block, using just this part of my inode block. The 15th block points to a triple indirect block that points to blocks containing double indirect blocks. So now I have 1K cubed times 4K that are stored in each of the blocks, or 4 terabytes. So I can have a file in theory as large as 4 terabytes plus 4 gigabytes plus 4 megabytes plus 48K. In reality, you can't really go quite that high, but who's got a file that large anyway, really? Okay, so let's talk about the new way of doing things. And this came about in ext4, and this is the use of extents. So what's an extent? It's a tree structure, and it contains 3 kinds of entries. It starts out with a header, and then you might have an index or a middle node in this tree. So it's not a leaf node and it's not the top of the tree. It's an index or middle node. And then at the bottom we have extents or leaf nodes. So each of these structures is 12 bytes long. The header we saw in a previous video in one of our examples contains a magic number, F30A, and then it has the number of entries that follow. After that, it has the maximum number of entries. In other words, how much space is there to store entries after this header? Then you have a depth. How deep does this tree go? If it's 0, this node points to data blocks, and if it's 1 through 5, this node points to other extents. Now, if you do the math, you'll find that you'll never need more than 5 levels. And then we have the tree generation that stored the version. The indexes or middle nodes are also 12 bytes. You have 4 bytes for a block. And that says this node covers this block and following. So what is this index for? It's for the following blocks. And then you will see a 48-bit value that's broken up by the lower 32 bits and then the upper 16 bits. And it has the block containing the node, the leaf, or another index that is 1 level lower in the tree. And that's pretty much all that's in the middle node. It just says, hey, here's the block that's covered by this node, and here's who's below me. I don't have anything terribly useful. I just point to somebody else. And finally, we have the extent node or leaf node. And it is, of course, 12 bytes long. And the first 4 bytes store the block that is first covered by this extent. And then we have a length. Now, the length is encoded in an interesting way. If the number is less than 32K, that means there are this many initialized blocks in this extent. And if it's greater than 32K, whatever is stored there minus 32K is the number of uninitialized blocks. Then we have another 48-bit value, and we have the upper 16 bits of the starting block and the lower 32 bits of the starting block. So when we put all of these together, we can actually build our list of clusters. And it's stored in this tree structure. And we'll see some examples of that in future videos. Well, that's all for this video. As always, if you're enjoying these videos here at Pen Tester Academy, please tell a friend. We'll see you soon.